topic of today is to give you an overview of frameworks. So as you'll quickly discover as you play around with Android, there's an awful lot of software that you get out of the box from using the Android environment to build your applications. And this software is organized in a variety of different ways, but one of the most interesting ways is something called a framework. So we're going to talk in this next set of material about different aspects of frameworks. We're going to talk about how frameworks support so-called inversion of control, where it calls you back when something interesting happens. You'll quickly learn about that when you deal with Android, as we'll see. Frameworks provide so-called domain-specific structure and functionality. Frameworks factor out a lot of common behavior, common control flow, common structure that you would otherwise have to write by hand, and instead you're able to use the framework to have that done for you. Frameworks also are often typified by being so-called semi-complete applications, where the bulk of the behavior is already there and you're customizing and filling in the blanks. Why do we use frameworks? Well, hopefully it's pretty obvious. Frameworks provide great support for extensible reuse of design and code. So of course you'll be using lots of code reuse when you use Android, but you'll also be using lots of reusable design artifacts as well. And those are the kinds of things we would have talked about in CS 251. Those of you, I realize some people here haven't taken 251 or haven't taken it from me. The course is going on simultaneously to this class. Christoph's teaching it. We're putting the videos up for that as well, so you're welcome to follow along. But we're going to cover all the material about patterns that you'll need to know from 251 in this course. So if you have not taken 251, you'll get a chance to learn about the key topics. If you have not taken 251, though, I strongly encourage you to take it at some point because it gives you a lot of deeper coverage of the material we're going to talk about here. And the other thing that patterns do and frameworks do, and we're going to talk a lot more about this when we get later on in the course, is they implement so-called pattern languages, which are a network of patterns that provide a vocabulary and an orderly process for resolving software design challenges in particular domains. So we'll talk a little bit about that. 251 goes into pattern languages in a much more detail. The other thing we're going to do is, as we talk about all the different framework concepts in this series of slides, we're going to give examples from Android wherever it makes sense, so you can start to see how Android reifies or embodies the concepts we're discussing. We'll also then come back later when we talk about the specific details of the different Android components and frameworks, activities, services, and so on. And we'll explore these concepts in greater detail, but I'll just give you sort of an overview at this point. Okay, so let's switch over and start talking about frameworks. So what we're going to do in this set of material is first help you to understand why hardware and networking hardware has traditionally gotten better, faster, cheaper in a more regular pace than software has done. It's important to understand that. And we'll also describe some of the key characteristics of frameworks and explain how they help to improve software productivity and quality of code. So by the time we're done with this, those are some things you should be able to understand. And the quiz next week, on next Wednesday, will help to ensure that you're following along with this kind of stuff. As I mentioned before, along the way we're going to give some pithy examples of frameworks using Android, but we'll cover this in much more detail later. So if you take a look around, if you step back and you look at the computing field over the past 3 or 4 decades, there's some interesting trends that have occurred. When I first started out as a software grad student back in the mid-'80s, fast meant 25 megahertz computers. That was sort of the high end at the time for things you would typically get if you were a grad student or if you were someone who was working in the field. Nowadays, we've obviously got things that are a heck of a lot faster than that. We're up in the gigahertz ranges. The low gigahertz ranges is pretty typical. Likewise, when I first started out with accessing networking resources from my apartment as a grad student, we were really happy when we had 2400 baud modems. They were so much better than those 1200 baud modems we started out with. I can't even begin to imagine the pain of using a 2400 or 1200 baud modem anymore. It just crawled. But back in those days, we were pretty excited about that. So things have obviously gotten way faster. It's pretty much common nowadays. You're going to get tens of megabits of network bandwidth through your Wi-Fi connection. If you have Ethernet, you're probably getting 100 megabits or more to your desktop. So things are getting pretty fast. if you look at where we're headed over time, there was a point at time when we thought, well, we're just going to get faster and faster processors. That's not really happening too much at the moment, largely due to some of the limitations of the growth of Moore's law. That may change at some point, but at this point, the low gigahertz range seems pretty typical. On the other hand, my smartphone that I'm getting, which is a Galaxy S4, has got a quad processor. I think it's close to 1.5 to 2 gigabits, or 2 gigahertz processor, so they're getting pretty good. Where we're headed, of course, is lots more cores. And you'll see that one of the things we're going to talk a lot about in this course is how to harness the power of all those cores by using various kinds of framework capabilities to program multi-threaded and concurrent applications. So it's clearly the case that things are getting more plentiful as far as processor cores going, even if the processors aren't getting that much faster. And I wouldn't be surprised if over the next decade we're going to have hundreds or thousands of cores, pretty commonplace in the computers we buy. It's almost impossible these days to buy a computer that doesn't at least have a dual-core processor in it. You have to really work hard at it. And even on the smartphones, we're getting quad cores as pretty much par for the course. If you take a look at the networking bandwidth, it's going to keep getting more and more plentiful. The wireless range is going to get much better. There's talk about 5G networks coming to your phone, which is very, very high performance types of things. So this is great. One of the ways we describe this phenomena, this better, faster, cheaper in the hardware space, the networking space, is the concept of commoditization. If you haven't had a chance to think about commoditization before, you should spend some time thinking about it. I've got a little paper I wrote many years ago. It was a part of a dedication I was giving when I was working at University of California, Irvine, talking about the impact of commoditization on our lives, our professional lives. And it's worth at least exploring just a little bit because it's going to have a big impact on the kinds of things you would do in the future. We're not going to talk a lot about commoditization here, but be aware that there's tremendous commoditization taking place at the hardware and networking layers, which means that you can get this technology better, faster, cheaper at a regular rate, which means that people who are in that space have to come up with new and innovative ways to differentiate themselves from competitors. In contrast, software is often characterized by being buggier, slower, and more expensive than hardware. So if hardware gets better, faster, cheaper, oftentimes people's experience with software is it's buggier, slower, and more expensive. And it's a really fascinating phenomena to look at what's happened here. This is particularly true if you start looking at places that can't easily use off-the-shelf solutions to meet their needs. If you're able to use off-the-shelf solutions for software, then it is getting better, faster, cheaper. But if you have to go and build custom solutions, which is the case in the aerospace domain, it's the case in the power domain, it's the case oftentimes in the domain of defense and avionics systems and so on, software is just this enormous boat anchor that people have to carry around with them, and it's a big problem. One of the things that you see as a consequence of this is there's all kinds of books written about software runaways or software death march or software development failures. And if you take a look, especially again in the sort of the custom software space, a very, very large percentage of big software programs tend to fail in spectacular ways. You don't have to spend much time looking around the internet to find out that this is a real problem. It's particularly a problem in domains where you're trying to write mission or safety critical software. Software where the right answer delivered too late becomes the wrong answer. So again, power grid management, financial services, air traffic management. You probably saw just a couple of days ago, Wall Street was shut down, trading on Wall Street was shut down for a little while. I read one of those funny, the Dos Equis guy, the guy who says, I don't often drink, but when I do, I drink Dos Equis. There was a similar meme that said, I don't often test my code, but when I do, I bring down Wall Street, And so there's lots of other examples of where we rely on software, and when it doesn't work, there's all kinds of consequences that are bad for that. I wrote some articles, again, you might want to take a look at talking about some of the issues in this space. And if you watch the Coursera videos, there's a whole big module about all these issues. So it's worth taking a quick step back and asking, why is it that hardware and networking gets better, faster, cheaper at such a regular rate in contrast with software? And then the most important question that comes as a follow-on to that is, what can we do to make software have properties that are more like hardware? So one of the characteristics that make hardware better is that the advances in these areas typically stem from the maturation of standards and reusable interfaces, protocols, and modeling tools. When people go ahead and they build the x86 next implementation of x86 platforms from Intel or AMD, they don't start from first principles. They don't throw away what they've done. They don't create a whole new set of instructions. Instead, what they do is they keep the instruction set relatively fixed, and they work on ways on getting more transistors onto a chip, or deepening the pipeline, or improving the clock speed, or having more cores, or improving the fabrication. And they use a lot of design tools, design automation tools, CAD tools to do that. And so people don't have to keep reinventing this infrastructure all the time. They're basically pouring billions of dollars of R&D into improving a fairly stable set of instructions. Likewise, if you're building IP networking equipment, routers and switches and so on, you're Cisco or Juniper or Huawei or whoever, you don't start by reinventing the protocol every week. You don't start by re-implementing things from scratch. Instead, you find a way to put the packet forwarding into hardware. You put the packet routing into firmware. You find ways of being able to improve the processing of the protocols at higher and higher line speeds and so on. And so there's a tremendous amount of historical expertise that gets leveraged and amortized, and people who build that equipment just keep making it better and better. It's really quite amazing. In contrast, in the world of software, we don't tend to do those kinds of things. People are forever reinventing the wheel in this space. Many years ago, I was at a conference, this is probably 20 years ago or so, and I was listening to Grady Booch give a talk about the Booch components, which are a set of components that you would use for writing reusable software back in the late 80s and early 90s. And he was talking about the way in which they had reusable class libraries for C++, and you could have linked lists and stacks and queues and heaps and so on, and you could take these things off the shelf, and it was so nice and so reusable. And as I was listening to him talk, he gave a very good talk, a couple people sitting ahead of me that were from a company were saying, why would we ever want to do this? We could easily rewrite all these components ourselves in no time flat. What's the point of having to buy them from somebody else? And of course, the ironic part is it might not have taken that much time to rewrite that stuff, but then who's going to document it? Who's going to maintain it? Who's going to optimize it? Who's going to do all the other things? Who's going to figure out what happens when the world changes in some way and a new platform becomes important and your implementation done from scratch doesn't port easily, and so on and so forth. And there's just the whole issue of reinventing the wheel and redoing things. So there's a lot of inertia. A lot of people tend to like to do this kind of stuff. If you take a look at the smartphone market, or the phone market, not just smartphone, but the phone market, for many years, that's the way people build software. If you were companies like Nokia, building out the different phones they had, the different versions of Symbian, for example. If you were a company like Motorola, building out the various versions of the P2K-based feature phones and just regular flip phones that they did back in the day, pretty much every single piece of hardware had customized software developed for it. Even if you were developing things using, say, Symbian, which had, nominally a pretty common set of interfaces, the software was almost always very different. And it should be no surprise that in that space, the companies that built very ad hoc software solutions are now the also-rans, by and large. Companies that were not able to figure out how to improve the experience of building software have fallen further and further behind. Who's ended up cleaning up in this space? The companies that had tremendous software expertise. Apple, Google, people taking the Google code and customizing it for various hardware form factors. And those guys have figured out how to keep a pretty common base of software and moved away from everything done in a completely proprietary, tightly coupled manner on top of the hardware, and done it in a different way. Why was it bad to do the hardware and the software in such a customized way? Because what happens there is you have to spend this time manually rediscovering, manually redeveloping all this different capability, and then sustaining it in all the different hardware variations, which very quickly becomes out of control. Whenever you make a change, whenever the hardware changes, whenever the requirements change, a lot of work has to be redone, and that's because everything's written in a very tightly coupled way. It's very brittle. There's all kinds of issues with security holes. There's all kinds of issues with performance and portability and so on. So it's just like vertical stovepipes of spaghetti code. What's happened over the past 5 to 6 years in this space maybe going a little bit further back to the mid-2000 timeframe, is people increasingly are building apps on top of reusable frameworks. A framework is an integrated set of components that collaborate to provide a reusable architecture for a family of related applications. It's kind of a mouthful, and we'll talk a lot about the different details of that definitions, but the key points are integrated set of software components. In other words, the pieces don't exist in isolation. They're meant to work together. And component, by the way, the word component here could be class, object, function, etc. There's some flexibility in that term. And these components collaborate. There's common control flow. There's common structural behavior and interactions and dynamic communication taking place between things. There's a reusable architecture, the architecture being basically the set of components and the control flow and the way they're configured. And they provide a family of related applications. Family in this context means there's a lot of things that are similar. They inherit common properties. They inherit common characteristics. They have more things in common than they do different, but there's also differences that exist as well, just like your family probably is like that too. So if you take a look at the slides here, you can see how these things basically give you layers of abstraction, much more commonality, and now when you build different kinds of products, you have different phones provided by, say, Samsung versus HTC versus Huawei versus Motorola. They're much more common in the infrastructure, and you're programming apps at the variable part of the solution space. Frameworks give you a real benefit in the form of something called systematic reuse, which basically means that you think ahead of time about what the commonality parts of your solution are, what the variability parts of your solution are, and then you provide software frameworks that embody that commonality and variability, thereby factoring out a lot of domain-specific and domain-independent parts of the software so you can leverage that and use it yourself. There's a nice article I wrote many years ago that talks about systematic reuse and some of the pros and cons of that. So let's explore some of the key characteristics of frameworks in a little bit more detail. So we'll also talk more about this later, but one of the first things to remember is that software frameworks are different from other forms of reuse. We'll talk more about those forms of reuse. You have undoubtedly been exposed to some of these other forms of reuse. If you took 251, you were exposed to things like generic programming, class libraries like STL, and so on. And that's one form of reuse. That is not frameworks, as you'll see here in a minute. So let's talk about this. There's also an article that appears on my website that talks more about some of the properties of frameworks. Feel free to take a look at that. I'm not going to quiz you on the details in the article, but if you're interested in learning a bit more about what I'm about to talk about, it's a good place to take a look. So one of the first distinguishing characteristics of a framework is it provides so-called inversion of control. Now, there's a lot of different ways to understand inversion of control. I'll explain it from a technical point of view in a second. But one of the things that people often think about when they talk about inversion of control is the Hollywood principle. And if you take a look at this article on my website, you'll see a description of an article written by the late John Vlasides talking about the Hollywood principle. And the Hollywood principle says, don't call us, we'll call you. So think about Hollywood Moogle, right? You know, you're an aspiring actor or actress and you want to make a break, and the Moogle says, you know, don't call me, I'll call you when something comes your way that looks like it might be worth your time to be an actor or an actress in this film or TV show. So the key idea here is that frameworks have inversion of control where the framework owns the event loop. The framework's going to spend some portion of its time waiting for something to happen. And that something to happen is typically fairly low level. It's waiting for a touch event to come in from the screen. It's waiting for key press to come in on a physical or virtual keyboard. It's waiting for a mouse movement or a voice command or something or other to take place from the outside world. And once it figures out what's happened, it's going to go ahead and route that event. It's going to detect the event. It's going to route and so-called demultiplex that event to the appropriate pre-registered event handler. And then it's going to go ahead and dispatch a method on the event handler that you provide as an application developer or a service developer to do something interesting when that event occurs. So the inversion of control is that you don't own the event loop. The framework owns the event loop, and it calls you back when something happens. Now, that is quite distinct from what some of you may have been experienced. Obviously, anybody here who's programmed Android or iPhone, I'm not talking to you because you've already experienced this, but if you haven't spent time in this environment, if you've mostly spent time programming the kinds of things we do in 101, 201, even to some extent 251, a lot of those apps are self-directed. They themselves, the applications, own the event loop. They decide what's going to happen next. That's not what a framework is about. In the framework environment, the framework owns the event loop. It decides what's going to happen. There's lots and lots of examples of inversion of control in Android. The most immediate one that you'll run across as soon as we do the first assignment involves the callbacks that take place to handle lifecycle activities. Lifecycle activities occur when you launch an app, or when you have one app launched or one activity launched over another activity that's already running, or when an activity decides to shut down. And these get presented to you in the form of these on callbacks, on create, on start, on resume, on pause, on stop, on restart, on destroy, and so on and so forth. And so the framework, the Android framework, is keeping track of all this stuff, and when those events occur, it invokes methods that you are responsible for doing something about in the applications that you write. So that's a good example of inversion of control. You will see lots and lots and lots more of examples of inversion of control throughout Android. Services work this way, callbacks from content providers work this way, broadcast receivers work this way. Just about everything in Android works that way. And one of the characteristics of this is when you write an Android app, you're actually restricted from blocking the main thread of control for any length of time, because it wants to have the ability to call you back when something that has occurred takes place to inform you about it. And if you don't do this, you get the dreaded application not responding error. And we'll talk more about that. You've got an exception that says you're blocking things. You're being too self-directed as opposed to being inversion of control driven. The next thing that frameworks provide is so-called integrated domain-specific structure and functionality. So one of the key ideas here is that frameworks are not just about domain-independent capabilities. They're actually targeted for specific types of domains. And you'll see that we're going to talk about a couple of different types of domains. One kind of domain that frameworks should be characterized for would be so-called application domains. Things like electronic trading systems, things like social media, things like mobile applications. Android being a great example, or iPhone, the iPhone programming environment, iOS, being another great example of something that's tailored for the domain of mobile apps. If you're a mobile app developer and you're programming Android, the frameworks it provide you with all kinds of things that you've got to think about as a mobile app developer. Interacting with users, talking across the network, dealing with information that comes from sensors on the device like the GPS, where are you, the location, accelerometers, all kinds of other things that come your way are very, very customized for the domain of mobile application development. There are other kinds of domains as well, and Android has these too. These are more infrastructure-oriented domains, so things like database access, database management, networking, things like user interface interactions. Those are more kind of infrastructure types of things. They're usable in a broad spectrum of domains, but they are also frameworks in that context because they own the event loop. They have the thread of control. They do things that are relevant for things in that particular domain. Let's take a quick look at a piece of Android that demonstrates the concept of domain-specific structure and behavior. And this is something we're going to cover in a lot more detail later, so I'm going to go through it very quickly here. You'll get some chance to program with this really early on because it's a powerful framework that exists in Android. And it's something that's called the AsyncTask framework. And the AsyncTask gives you a bunch of abstract classes that you are responsible for customizing through inheritance. One of the abstract classes it has is the AsyncTask class itself, which provides you with a class interface that gives you a number of different methods and parameters to run certain activities in a background thread to avoid blocking the main thread of control. This is a generic type in Java. You can parameterize it with certain things. You can give it the type that's used to run in the background. You can have a type used to indicate progress. There's a type that's used to indicate the result that occurs by the time you're done executing this async task in the background. So those are some of the parameters that can be plugged in here to this abstract interface. There's also a template method. Those of you who are familiar with the template method pattern from the Gang of Four book, the template method pattern is a pattern whose intent is to define a skeleton of an algorithm, leaving certain steps in the algorithm to be provided by subclasses. So the particular template method that we have here is called execute, and when you call the execute method, it calls a number of different hook methods automatically. It first calls on pre-execute, which gives you a chance to do some initialization startup activities before it gives you the ability to run the processing in the background. It calls the do in background method in a background thread, which is not the same thread as the main thread of control, and you can do long-running computations in that thread without blocking the main thread of control. There's something called on progress update, which is called back when you decide in the background that you want to report some information to the main thread of control, like maybe update a status bar that's indicating how much of processing you've done. And then finally, when you're all done with your do in background method and you return, the on post execute hook method gets called back, delivering the result that was computed running in the background. And that then executes back in the main thread of control again. So kind of cool. It's a great example of a framework, the AsyncTask framework. It's got inversion of control. It's the one running those callback hooks. It's domain specific. It's customized for people who want to write applications that run in different threads of control in Android. And it's also interesting because it's an example of the template method pattern. So you're basically given the chance to override and customize certain hook methods. I'll talk a bit more about this again a little bit later. The last piece of the puzzle, the last key defining characteristic of a framework is the fact that they are so-called semi-complete applications. And what that means is that they have certain hooks that can be customized in order to be able to do specific things that are particular for the context, domain, application, service, however you're applying the framework, that the designers of the framework couldn't possibly have known about because they didn't have the insight as to how you were trying to apply those pieces. So what makes them semi-complete is that they do an awful lot of work on your behalf, but wherever there's something that they don't know what to do, they give a hook to you. So think again about what Android does with its activity mechanisms and its activity framework and its lifecycle management. The Android developers know that when you create a new activity, something needs to be done to initialize it. They don't know what that something is, so they give a hook called onCreate that gets invoked automatically by the Android framework manager and the activity lifecycle manager, and that's where the application code gets done to do the application-specific initialization. Likewise for pausing and resuming and stopping and starting and destroying. Giving a very simple example here, continuing on with our async task theme, if you want to come along and take the existing async task framework capability, which is got this domain-specific structure and functionality, and you want to customize it for your particular needs, what you do in this particular case is you subclass a class from async task and you override one or more of those hook methods to do whatever you want to do. Later, as we get further on in the course, we'll have an assignment, several assignments where you're going to be writing sort of a download service that downloads content from websites, and then you'll end up displaying those things after they've downloaded in a main thread of control. And one way we're going to do this is by using async tasks, and you'll end up writing a download async task, which when you start it, you'll give a URL. It will go out in the separate the background thread of control, download the content in the background thread, and when it's done, it'll come back and tell the main thread of control, I've downloaded the content, here's how to display it, or here's what I want you to display. So that's an example of basically completing or customizing or specializing the framework by instantiating subclasses and instances of subclasses and overriding those hook methods to do your bidding as you happen to want them to work. So that's a good example of a semi-complete application. Async task doesn't know what your hooks need to do, but it does lots more stuff. By the way, the async task code is available in open source form in the Android release itself. And if you want to learn how this works, I strongly encourage you to take a look at it. It's really quite fascinating. It has lots of interesting patterns in it. It uses futures. It uses an active object-like model internally to send around these different elements when you invoke operations, and it's either spawns a thread or has a pool of threads. We'll talk a bit more about that later. And it uses a bunch of interesting patterns to implement the framework itself. So to summarize this first part, the quality of software and the productivity of developers of software has historically lagged the productivity of people building hardware and networks. There's a couple of different reasons for this. Some of the reasons are because software has certain inherent complexities that hardware developers don't have to wrestle with. Hardware in many ways is intentionally designed often to be fairly straightforward. You want to keep it fairly simple. You want to make it so you can have a RISC-like architecture where there's one instruction executed per clock cycle. And so you keep the instruction set deliberately fairly simple. And so that means it's easy to write fast hardware, but it makes somebody else responsible for figuring out how to schedule this thing, deal with pipelines and delayed branches and other kinds of optimizations that have to be done by software. Moreover, other inherent complexities of software are there because we're trying to keep the hardware fairly simple, and we deal with that by making the software more complicated. So various kinds of concurrency mechanisms, networking, fault tolerance, reliability, those things are deliberately built at the software layer because there's a lot more opportunity for variability and customization in software. It's just inherently easier to develop those things without having to bake it into the hardware and make it very brittle and difficult to change. There are other reasons why hardware is better too, though, that are not because of the inherent complexities of the software domain. It's because people just tend to reinvent things willy-nilly without thinking about the consequences. So one of the great contributions of Android and iPhone and so on is getting people to appreciate the benefits of systematic reuse for the applications they develop. Even if they themselves may not be framework developers, they are framework consumers. And the trick is to do that in an effective way. Again, this is very important for more complex systems. You'll see that initially when people build phone apps, each app is fairly self-contained. Each app has relatively few dependencies on other kinds of things. You can write Android apps, and we'll write Android apps where you actually leverage a lot of existing capabilities using some of the cool Android framework capabilities like the Intense framework. But there's a lot of other stuff in Android that it makes the apps fairly self-reliant, and they don't typically interfere with each other a whole heck of a lot. As you start trying to write more sophisticated types of systems, you'll find that there's a lot more interaction between the services and capabilities that are provided. And that makes it even more difficult to do things in software, motivating even more the importance of software frameworks and systematic reuse. Enormous amount of cost occurs from reinventing things without really stopping to think about what you're doing. Again, great contribution of the smartphone domain is helping people do a framework and apps model where the framework is relatively fixed and we focus on apps. And we have as a consequence of this things like app stores and marketplaces and tremendous innovation in that space. People sometimes think, oh, gosh, reusable software, it's going to be the end of innovation. People ought to be able to write this code from scratch because it'll be so much faster, so much leaner, so much tighter, and so on. Complete bunch of gooey, bunch of hooey. As you take a look around and look at what's happened over the past decade or the past 3 or 4 decades, as we have got higher level abstractions like frameworks, the productivity and the economic value of software has gone through the roof. You take a look back in the early days of computing, back in the late 50s, when people were writing in assembly code. People were writing in Fortran at the end of that time period, the early 60s and so on. There was actually a concern with a lot of programmers that as we moved to automation, as we raised the level of abstraction, that there would be less opportunity for developers. People thought, oh gosh, I'm a great assembly language programmer, and this compiler stuff, that's going to put me out of a job because people are going to automate this, and I'm not going to have to allocate registers by hand. I'll have a compiler to do it instead. Well, if you take a look at what happened, as we raised the level of abstraction, there was an explosion in economic value for people who understood software because we were no longer sitting there wrestling with how to control the hardware, which is what people spent their time doing in the early days. We were spending time providing value for the customers. And over time, this has just gotten more and more lucrative. And the more we can meet the needs of customers, the more we're going to get paid, as more we collectively get paid and keep the job security of this profession, because you're able to do things that are more interesting. Now, having said that, if you just continue to build yesterday or 3 or 4 generations before solutions and the world moves on, you're quickly going to get disintermediated and commoditized. The thing to do is be able to stay on top of the new advances, which again is something that we'll talk a lot about later in the course. Frameworks improve productivity and quality of software development by being able to reify proven solutions in the form of designs and implementations in selected domains. So needless to say, things that you find in Android didn't just spring up overnight. There's many, many patterns that you've learned about before or will learn about that are embodied in Android. People who built Android had a lot of experience with other kinds of environments, the BOS, other systems, so there's a drawing upon the heritage. They obviously leveraged tons of experience by adopting Java and many of the Java class libraries as part of the overall environment, because that kind of came along for the ride. And there's many, many other things. If you think back to the layer cake diagram of Android, lots of other stuff that comes along for the ride too. Linux device drivers, libc, people doing native code development and so on. So then they could spend their time developing frameworks that are customized for the domain of mobile application developments. Another huge contribution that frameworks make is they help to amortize quality assurance efforts. This is the other thing people miss when they think, oh, I could just sort of hack that code up over the weekend and I'll be able to do what could be done if I bought this software package or this library or these frameworks or this toolkit. The problem there is that as things get more complicated, it's essential to be able to find a way to scale and amortize quality assurance. In fact, if you're doing your agile development properly, you're spending the bulk of your upfront time writing unit tests to make sure the code you write is going to stay correct over time. This is something that's not well understood. People tend to write code without thinking about the consequences and the costs of maintaining it and sustaining it over time. And a huge part of that cost is making sure that as you add new capabilities in response to new requirements, and as you move to new environments and port to new platforms and new languages and new tools and new operating systems and new middleware, that you don't break the pre-existing commitments to what's already there. So one of the great things about frameworks is if you set it up properly, you can automate a lot of the quality assurance, the testing, the running of regression tests, the adding of additional tools, running memory checking tools, running code coverage tools, running vulnerability detection tools, and so on. And that's one of the things we're starting to work on a lot more here in Vanderbilt, is giving you guys exposure to that earlier on in your curriculum. So 251 now, requires people to run Valgrind before submitting the assignments, and getting into that habit is essential. Frameworks that are mature have these things built in and automated, and we'll talk more about that later on in the course. Having said all that, there still is a long way to go to reach the degree of automation and tool support in the software world that people who build hardware have long since taken for granted. If you are building a chip, if you're responsible for the next generation mobile chips or chips from companies like Intel or AMD or whomever, you don't just start by wiring transistors together or taking various pieces of hardware and soldering them. If you go out and watch the Steve Jobs movie, one of the things that was most interesting was an awful lot of their early experience was sitting in Steve Jobs' parents' garage, literally soldering together the boards for the computer. It was that non-integrated back in those days. Nowadays you're getting system on a chip, network on a chip. It's coming pre-packaged, boom, boom, boom. People who build those technologies are using model-based tools for almost everything they do. As a consequence, they can do a tremendous amount of simulation and analysis to verify the absence of certain hazards or to verify certain properties are maintained in the software or in the hardware, and then they simply synthesize the results, and it's largely an automated process. There's a lot of cool stuff going on here at Vanderbilt along these lines, model-based techniques. We have a course, CS 388, that you might want to look into. It's about model integrated computing, gives you one way to do that kind of stuff. We're also using those kinds of tools, domain-specific modeling tools, domain-specific modeling languages, on a variety of interesting research projects, such as the Advanced Vehicle Make project, or AVM, which is a DARPA-sponsored project for being able to essentially synthesize and create and manufacture complex vehicles from design specifications. It's kind of 3D printers on steroids to make vehicles from design specs, rather than going out there and, with a hammer and bending the metal manually. So a lot of stuff still to be done. So that's the end of the first framework overview slide. Slide set. Let's go ahead and talk about the second one. So in this particular set of slides, we're going to talk about how frameworks compare and contrast to other forms of systematic reuse. And I'll talk about frameworks and how they relate to other things, some of which you're probably very familiar with, things like class libraries, other things you may be familiar with from other work you've done, things like component middleware. And then we're also going to talk about the different categories of frameworks. There's a couple of different categories. There's black box frameworks, white box frameworks. Oftentimes in the real world we get a little bit of both in our solutions, and I'll show you some examples of that. And again, we'll show some examples from Android to illustrate these various points. So let's start by talking about different kinds of software reuse techniques. If you go back far enough in the mists of time, you'll see that some of the first forms of reuse people did was in the form of reusable function libraries. So not surprisingly, given the origins of where computing came from, people traditionally were using software and computers for mathematical operations. So it would be no surprise at all to think about the early days, people's big contributions from a reuse point of view were reusable function libraries doing mathematical stuff. Nowadays, this is pretty much par for the course. There's numerical analyses, algorithms out there in many different guises, many different forms. Nobody in their right mind, unless you're a numeric analysis PhD student or professor, would write these things by hand. There's all kinds of great stuff out there. You just take it off the shelf and use it. And that covered us up for about the first 15, 20 years of computing, depending on how you count it. Then in the 70s, or certainly in the 80s, people began to realize that reuse of functions alone was not adequately satisfying. There's only a handful of things, namely mathematical functions, that are easily expressible by a function abstraction where, for the most part, you pass in the state that you need in the form of parameters to a function. As we started to build bigger systems, people began to realize that there was relationships between many functions and the data structures they worked on, and having a function library alone was not adequate. So what happened in the 70s was Smalltalk, and then in the 80s with languages like C++ or Modula 2 or Modula 3 and so on, or Ada, I guess, if you, depending on how you count that, people began to realize that there were different ways of abstracting things. And so what became very popular was the concept of reusable class libraries. So good examples of this would be some of the stuff you'd find in Smalltalk and their class libraries, some of the things you find in C++ in the early class libraries, the Booch components I talked about before, more recently things like the standard template library, other parts of the C++ standard library, and of course the Java class libraries. So class libraries are typified by a couple of things. They have classes, of course, and classes are the units of reuse in a class library. And a class, as you all know, combines a number of methods and some shared state, which is typically hidden from the clients or the users of the classes by making them private or protected. In a class library environment, the classes themselves are typically passive. And what that means is that you invoke an operation, you, the application developer, decide when to invoke an operation on the class or the object of the class, and it borrows a thread of control, does its thing, returns the result. Classes just sort of sit there, or objects just sort of sit there, and you invoke operations on them. Moreover, you typically are in charge of the event loop of the application. So you decide what gets done next, how often it gets done. You control the flow of behavior through the application. And another characteristic of the class library environment is the classes, by virtue of the fact that they are fairly standalone, often represent domain-independent abstractions. Things like strings, things like heaps or sets or maps or vectors and so on. Mathematical entities again, files, fairly straightforward things you would use in almost any domain that you happen to run across. Now, class libraries are better than function libraries in many ways, for most things, maybe not for math operations, but they're certainly better in lots of ways. But they only get you so far. They only solve a very small part of the problem space. And one of the things they don't really deal with are some of the things that motivate the use for frameworks. So as we mentioned before, frameworks are an integrated set of classes that cover domain-specific capabilities. They provide reusable architectures for families of related applications in a particular domain. So as you can see from the picture here, what happens is a lot of the stuff that used to be done by the application developer gets refactored and placed into the framework. And what you have instead is you have the application-specific functionality shrinking or perhaps growing because you're able to do more stuff, but you're putting more and more of the processing, the structure, the canonical control flow, the default behavior, the default interactions and communication between elements of components that are part of the framework themselves. And you actually may have multiple frameworks. As we talked about before, they're often driven by callbacks to registered event handlers. Now, there's no reason why you can't combine class libraries with frameworks. In fact, most frameworks, in fact, all frameworks probably, are implemented using many, many class libraries. So that is certainly true in Android. If you take a look at what Android has, you've got all the Java class libraries for doing various things, for threading, for file I/O, for network I/O, and so on. And then various frameworks are built around that, and they reuse those elements. Likewise, the application-specific code that you write also can use the elements of class libraries as well. But the difference is that the model of frameworks is one that is driven by inversion of control. They're more domain-specific. They're semi-complete applications. The frameworks are more active. Objects are getting called back when things happen. It's just a little bit more, it's a little bit more customized and tailored for particular domains. Lots of great stuff you can read about frameworks. Ralph Johnson from University of Illinois, Urbana-Champaign, Gang of Four author, famous Smalltalk programmer and researcher, has written extensively about frameworks, and lots of really good insights come from looking at some of his papers. The last thing we'll talk about here, just briefly, just to provide some context, is component-based and service-oriented architectures. In many ways, these kind of combine aspects of class libraries and frameworks. The main idea is to provide something called a component, which is something a bit like a class, but the main difference is that unlike traditional classes, which are fairly small and domain independent, components are actually more black box encapsulation units that can often be transparently distributed or replicated or used in a concurrent environment without having to think much about how the implementation works under the hood. Moreover, components or services are typically plugged into middleware that allows you to be able to stretch the processing capability across networks, across concurrency boundaries or host boundaries. Moreover, component or service-oriented framework environments, or they're built on top of frameworks often, but they often provide additional capabilities to assemble and compose the components and services together via various forms of metadata, things like XML descriptors of various flavors and forms. And so what you find yourself doing as a developer in a component environment is less writing lots of software, but rather taking bits and pieces of things, some of which you wrote, some of which you got off the shelf, and wiring them together using the metadata for the assemblies and the composition. And so typically you'll find a tremendous amount of tool support, things that are baked in to the development environment that help to arrange the various pieces. Android provides a lot of this stuff as well. As we start taking a look at how the integrated development environment works in Eclipse, you'll see that there's a lot of things taking place behind the scenes to integrate the various resource files, the XML files that describe layouts and abstract away from specifics of strings and their values to provide support for internationalization and so on, and other characteristics are all done for you, and it wires together your application elements, your components, in all kinds of interesting ways that you don't have to think too much about unless you really care about it. There's a bunch of articles about component middleware available on my website, so you can learn more about the approach there. So, as a general rule of thumb, frameworks are more flexible and powerful than class libraries and component and service-oriented architecture style ways of doing things, but they also tend to be more complicated to develop and use because there's more flexibility offered to you. And so the right choice, and we'll talk about this later when we do a little bit of evaluation, depends on what it is you're doing. If you are working in a team of expert developers and you need to have a lot of power to customize and tailor your solutions for different clients, for different contexts, different requirement sets, frameworks may be your cup of tea. if you're really cool, if you work for Apple, or you work for Google, or you work for other companies, you may be building frameworks. But that's beyond the capability of many, many, many developers. So it's often the case if you're an application developer and you're just trying to get the job done, you want to work 9 to 5, you don't want to spend all your time trying to wrestle with all the complexities of callbacks and inversion of control and concurrency and distribution, then you may prefer to use a different model of systematic reuse. You may prefer to use a component-based or service-oriented approach, which tends to kind of sand off some of the sharp edges and shine a light in some of the dark corners that plague people trying to build and use frameworks. So you'll see that there's pros and cons. Things like Android give you a variety of different ways to go about this, but if you're doing straightforward Android programming, you are programming to frameworks, and you have to get accustomed to some of the things that implies. There's a couple different categories of frameworks. One kind of framework is called a black box framework. Black box frameworks only require an understanding of the external interfaces of objects or classes. So you can use them without really having deep knowledge of how things work under the hood. And you typically use black box frameworks by assembling and parameterizing objects using composition or some other means to bring things together and assemble them. White box frameworks, in contrast, require some degree of an understanding of how the framework is implemented internally. What are the hook methods? What do you have to customize and override? How do you do this? What's the protocol for doing that? And typically you work with white box frameworks through subclassing and overriding of various methods. Now, as we'll see later, there's a lot of subtle variations here, and in real world we often have a little bit of each. There's a real nice discussion about this concept on black box and white box frameworks at this website, which is one of Ralph Johnson's former students named Brian Foote, who's an expert on patterns and frameworks and has been working in this area for many, many years. He's also a very engaging writer and speaker, and if you ever have a chance, read some of his stuff. He's written some really, really good articles about systematic reuse and getting people to use software off the shelf and so on. Each category of framework, black box, white box, uses different sorts of patterns. So for example, black box frameworks tend to use patterns like strategy or decorator, where you're going to reuse things more or less without having to know a lot of the internals of how things work. You just kind of plug in various elements. And we'll see some examples of that. For those of you who are programmers of C++ and the standard template library, that's a lot of black box reuse. It's not really a framework, but it's black box reuse. You're often plugging in template parameters using policy-based design, things like functors or other elements. And all you have to know is that the functor has an operator function call method. And whatever algorithm or container you're parameterizing this thing with just knows how to use those function calls in the appropriate way. It's a black box from the point of view of the user. In contrast, and you can see more about strategy pattern by looking at the Gang of Four book or looking online. Hopefully everybody here knows the strategy pattern. If you don't know the strategy pattern, we'll cover it later. I'll be happy to go over it in office hours or ask questions. White box frameworks, in contrast, tend to use different kinds of patterns. They tend to use a lot of things like template method patterns or state patterns, where you're overriding and filling in certain hook methods that get called back when something happens. So you have to know a bit more about how things work under the hood. You can take a look at template method. We'll look at some more examples of that when we talk more about how the activities and services work in Android. Many, many frameworks, and we'll look at an example here in a second, combine both white box and black box techniques. Android certainly has its share of that. As a general rule of thumb, white box frameworks are easier to develop because you don't have to anticipate all the different ways in which you're going to be using the different elements in the framework. You make it the application developer's problem to some extent to know how to customize and extend. But they're harder to use because you have to think about this as an application developer. You have to know how to inherit, what to fill in, what not to fill in, the order in which these things are going to get called. So there's a bit more work on the user's point of view, but it's a bit easier to develop. Conversely, black box frameworks are easier to use because a lot of those dependencies and interactions have been thought through for you already by the developer of the framework, but they're harder to build because you have to think about those things in more detail, and you have to figure out just the bare bone minimal set of interfaces and types and dependencies. So, not surprisingly, there are often not as many black box frameworks because it takes more work to do. We're going to look at two examples of white box and black box frameworks in Android, which ironically enough both exist in the context of the same framework. The AsyncTask framework in Android has elements of both white box and black box reuse. So here's a diagram that illustrates a little bit more about how Android's framework works under the hood, the AsyncTask framework works under the hood. And we'll first look at the white box dimension of the framework. So we have our execute template method, and when you call that, then the framework automatically calls back to the various hook methods, the on pre-execute, do in background, and on post-execute methods and so on. And the long-running tasks, as I mentioned before, have to run in the background. And things like on post-execute can be used to display the results of the long-running task when it's finished back on the user interface. Take a look here for more information about AsyncTask. It doesn't describe it in quite the way I am because it doesn't talk about black box and white box frameworks, but that's what's going on behind the scenes. Because it's a white box framework from this point of view, you have to come along and subclass it. You have to provide those hook methods. You have to go and inherit from AsyncTask and then figure out which methods do you want to override. And you have to understand a bit about how they work. You have to make sure that you don't do something stupid like try to write to the GUI from the do in background method, which is running in a background thread. And in Android, you're not allowed to do that. If you do that, weird things are going to happen. So you have to remember all those things. So that makes it a little bit complicated to use. The hook methods can be overridden. Here's a very simple example of this, where we're going to start out by displaying some kind of dialog in the on pre-execute method, prompting the user to enter a URL or something. After they enter the URL, we're going to go ahead and process that URL in the background in the do in background method, so that'll run in a separate thread of control. And when that guy's all done running, then we're going to pass back whatever we got, the bitmap image or whatever we downloaded, using on post execute, and then we'll turn around and tell because we're back in the main thread of control, say please go ahead and display this thing and dismiss the dialog. So there's a bunch of different kinds of things you can do here, and you have to know how to override and customize those various elements. In Android, the instance has to be created once in the UI thread, and you can only execute it one time. So here's an example where we might have a threaded download activity, and one of the methods we're going to have here is called run AsyncTask. We would connect this, of course, via the metaprogramming means we talked about before to some kind of click on a button in a widget, like some kind of view. And when that happens, then we get whatever the person provided to us, and we say go ahead and execute the task, and that'll go ahead and start things up and run the processing in the background thread. Conversely, here's an example of a black box framework that is also part of the AsyncTask framework. So it also provides support for black box use. And the way it does this is it allows you to come along and control the behavior of the number of threads and what their characteristics are, what priority they run at, and so on, by creating something called an executor. And the executor is used to actually create the context in which the threads are created and run. And the way that this works is that you can read the documentation. It's a little bit complicated because it's a black box framework. You have to think it through. And you can create your own executor, and then you can go ahead and set your executor, or you can use one of the predefined ones and make that be what the AsyncTask framework uses to execute and launch the threads. So there's a couple of different kinds of executors. There's a serial executor, which is what you get by default. There's a thread pool executor, which has a pool of threads, and then you can make your own custom executor, and as long as it conforms to the interface expected by the AsyncTask framework, you can just go ahead and plug it in to the AsyncTask framework, and it will use that as a black box whenever it needs to create and destroy the various threads under the hood. If you read the documentation, by the way, for AsyncTask, you'll see some interesting things took place over time. At various points in time, Android had sort of one thread of control running all the various async tasks, and then they said, well, that's kind of crazy. Let's have a pool of threads running these async tasks. Well, the problem was people who'd written their code to not understand concurrency all of a sudden had a lot of things breaking. So they, at some point along the way, they said, oh, that was a mistake. So they backed off, and now there's one thread of control again that processes all the different operations for the AsyncTask instances. But if that's too restrictive for you, you can go ahead and plug in your own executors to do the work using the black box framework capabilities. Okay. There's other examples. I've written pretty cool stuff that use both black box and white box frameworks, and if you really put your header into it, you can do stuff that combines elements of both fairly easily, and there's a paper that talks about that here. Okay, to summarize this particular module, frameworks give you a lot of power. They are going to give you a lot of systematic reuse. They're going to give you domain-specific reuse. You don't have to think a lot about the details. The framework does it for you. But they're harder to develop, and you have to be careful that you don't end up creating stuff that people can't understand how to use. So they're hard to build, and sometimes they're hard to use. We've been doing frameworks for a very long time. In my experience, the best way to build a framework and the best way to ensure that people can figure out how to use it properly is to guide it by the use of patterns, and more importantly, pattern languages. If you take a look, we'll talk about that later. And this course doesn't really go into pattern languages. That's more of a 251 topic. But we've done a lot of work over the years with pattern languages and using them to help guide the architecture and design and programming characteristics of frameworks. As a general rule of thumb, it's often better to take off-the-shelf frameworks and customize them rather than trying to build your own frameworks from scratch. Certainly nobody in their right mind these days would take something like Android and rip out the GUI framework and plug their own GUI framework in. I should take that back. Actually, a bunch of people did that. For a long time, people who are developing various kinds of variants of Android, say Samsung, they have their own specialized user interface called TouchWiz. And TouchWiz has its own sets of widgets and controls and so on, and it provides a custom skin over top of the reusable Android infrastructure. That is, of course, a major pain in the behind for Samsung, because every time Google comes out with a new release, they have to update everything. And that's why it's often been difficult for some of the phones to update to newer versions of Android when they come out, because there's lots of dependencies that the vendors have on their proprietary solutions that take a long time to retrofit. So one of the characteristics you're seeing increasingly is the use of pure Android phones. So things like the Galaxy Nexus, I think there's some stuff from HTC that's come out as well, where they try to have sort of the out-of-the-box experience for Android provided in their hardware environment, and that way when new releases come out, it's easier to upgrade. So there are still people who do crazy things like invent their own GUI frameworks, but it's less common, and it's a lot of work to try to maintain that in a customized way. As a general rule, using components and services that are more black box are easier for app developers to use, but they don't give you quite as much power. The metaphor here is basically saying, you know, a spoon and a fork and a knife are very simple to use, but they aren't as flexible as a Swiss Army knife, which gives you lots and lots of stuff. On the other hand, you know, if you've ever seen a Swiss Army knife with 70 different blades and things that come out, eventually you're sort of perplexed as to how to use this stuff. You know, what is it really good for? So there's a trade-off between simplicity and power. As a general rule of thumb, meant to be violated as needed under the right circumstances, I often encourage people to apply this funnel-like model when they're trying to do systematic reuse. You try to use off-the-shelf technologies down at the bottom as much as possible for what you're doing, because that can leverage the amortized efforts of really smart people who spend their time trying to figure out how to build these frameworks. That would be something like, you know, leveraging Android that you get out of the box from Google. And then as you go up the stack, the idea here is there's only a handful of people doing the stuff at the bottom. And as you go up the stack, there's more opportunity for customization and more opportunity for application developers, but they're providing things that are higher layer abstractions. So you would typically try to expose to the application developers something much more easy to use, like a scripting environment, something where you're plugging and playing stuff or using simpler languages that don't give you as much capability, as much power as Java or C++ might. And so they're able to program much more readily, but they're not being exposed to all the details and complexities. And it's really the job of the infrastructure developers to mediate the interaction between the off-the-shelf capabilities coming in from the framework world of commercial frameworks and the experience expected by the application developers. So a lot of bigger projects are typically organized this way. You have an infrastructure team, and they're responsible for doing customization of off-the-shelf things, plus some proprietary stuff to create an end-user experience that's easier to work with. There's also lots of good material you might want to look at if frameworks are interesting to you. We wrote an article about a decade ago that talks about the pros and cons and ease of use versus complexity of development and debugging of frameworks. And it really tries to give a balanced look at this particular technology.